Hello dear student, this is Devansha from LG Institute of Engineering and Technology. We have been learning the subject basic electrical engineering and we were in a discussion of AC circuits. So in our previous session, we have discussed about basic RLC components uh, individually and we have applied AC signal. After that we learn about the combination of R and L in AC circuits where we have connected resistance and inductor in series and we have applied AC signal. Same way, we have also discussed resistance and capacitor. We have connected together in a series and we have applied AC signal. So far throughout this discussion, we learn about the behavior of purely resistive circuit, purely inductive circuit, purely capacitive circuit and the combination of resistance and inductor and the combination of resistance and capacitor in series under the excitation of AC signal. We are going to discuss about the resistance, inductor and capacitor all we connect in a series and we applied AC signal, right? So here we are going to connect resistance, inductor and capacitor all together in a series under the excitation of AC signal. V is equal to Vm sin omega t. So again my aim is to check the behavior of resistance, inductor and capacitor while they are connecting in a series with respect to each other, right? So let's start the series RLC AC circuit, right? So you can see here in this circuit, resistance, inductor and capacitor, these three components are connected in series under the excitation of AC signal. So here we have applied AC signal Vt is equal to Vm sin omega t. My job is to find the voltage drop across resistance, inductor and capacitor, that is Vr is voltage drop across resistance, VL is the voltage drop across inductor and VC stands for the voltage drop across the capacitor. Point number 1 is find the relation between voltage and current and the phase difference. Point number 2, draw the phasor diagram and waveform. Point number 3, power calculation. Right. So far, since here we are going to connect R, L and C in series. So my first job is to define the phasor diagram of individual resistance, individual inductor and individual capacitor. Then I am going to combine all these three phasor diagrams in a one common phasor diagram that can justify the series combination of resistance, inductor and capacitor. So you can see here in this particular phasor diagram where the x-axis defines as the current vector. Since in a purely resistive circuit, here the phase difference between VR and current are same. That means both are in a same phase. So I have taken the vector VR is same position as vector current I. Right, but this is not case with the inductor. As in inductor, current is lagging by angle 90. So for this case, you can see here, the voltage across inductor VL is leading ahead by angle 90 with respect to current which is flowing in a circuit. Same way, if I talk about the capacitor, you can see here VC that is lagging by angle 90 with respect to current I which is flowing in a circuit, right? So throughout this phasor diagram, you can see here the one vector which is a current vector, within a same vector you will find the vector VR, right? But VC and VL both are in a opposite direction. So from this I cannot conclude in which direction you will find the actual phasor diagram. Since both vectors are in a opposite direction, so that means here I have to take total 3 conditions. So here you can see the current is taken as a reference as per this phasor diagram where VR is drawn in phase with the current. VL you can see is drawn leading by angle 90 and VC is drawn lagging by angle 90. So from this phasor diagram I can conclude with the three important conditions. Condition number 1 is VL is greater than VC. Condition number 2 is VC greater than VL, and the third condition, either VL or VC both are same. So condition number 3 is the VL is equal to VC, right? So if I consider the condition number 1, VL greater than VC, that means VL is nothing but I into XL and VC is nothing but I into XC. So here the current throughout the series operation is same. Condition number 1 is VL greater than VC, that means XL is greater than XC. Sorry, condition number 2, VC greater than VL, that means XC greater than XL, and condition number 3, that is VL is equal to VC, that means XL is equal to XC. Now all these three important points, that the relation between voltage and current and phasor diagram, then relation of voltage and current and phase difference between voltage and current, draw the phasor diagram, this is what the phasor diagram is, and power calculation of all these three conditions individually. So let us first try to understand the condition number 1. So here for ease of simplicity we have taken condition number 1 and condition number 2 as a case 1 and case 2, and we differentiate between these two. From this you can check the case number 1 where VL greater than VC, that means XL greater than XC. So this is what the phasor diagram is, that where you have a vector I, right? Within a same vector you will find the vector VR, but on a y-axis, since VL is greater than VC, so that particular vector magnitude we define as a VL minus VC, right? So you can see from this two vector you will find the resultant vector which is V, and all this are rotating in an anti-clockwise direction between two magnets. The theory is same. So if you apply this phasor diagram where you find the resultant vector which is VL minus VC in VL direction, right? So here the phasor diagram direction is in above the 0, but this is not case with the VC greater than VL, where XC greater than XL, that means the dominance or the reactance of capacitor is higher than the reactance of inductor, right? But for the case number 1, reactance of inductor is higher than the reactance of capacitor, right? So from this you can find the resultant vector V, right, here, and from this two phasor diagram you can conclude that for the case number 1, the resultant voltage V, which is leading by angle phi, which is a resultant angle, and case number 2 you can see the resultant value of voltage V, which is lagging by angle phi with respect to current, right? Again we can go for and just define the equation. So for first case, if you find total V is equal to under root VR square plus VL minus VC of whole square. Once you put the value as VL is equal to I into XL and VC is equal to I into XC, and you can find this value, and see here V is equal to I in bracket R square plus XL minus XC square, right? So this particular term I define as V is equal to I into Z, and Z defines the impedance of this case 1, where Z is equal to under root R square plus XL minus XC square, right? But if you check about the case number 2, where V is equal to under root VR square plus VC minus VL of whole square, right? So from this I can write the equation VL is equal to I into XL and VC is equal to I into XC. Then you can find the equation by V is equal to I of under root R square plus XC minus XL square, right? Since here you can take the impedance Z is equal to under root R square plus XC minus XL square, then V is equal to I into Z. This is what the common equation for case number 1 and case number 2. And further, if we define this terminology, you can find the uh, resultant angle phi, that is equal to, for case number 1 where XL greater than XC, then tan phi is equal to VL minus VC divided by R. This is from the triangle. Right, so if you apply here trigonometry in this particular phasor diagram, you can see here in this case number 1 and case number 2 phasor diagram, if you apply the trigonometry and find the value of phi for both the cases, you can see here tan phi is equal to VL minus VC divided by R. You can check here. So from this you can find the value of phi is equal to tan inverse I in bracket XL minus XC divided by I into R, where you remove the value of I, so you can find the resultant angle phi is equal to tan inverse XL minus XC divided by R. Right, so here once you apply Vt is equal to Vm sin omega t, you will find the value of current I is equal to Im sin omega t minus phi. Now why minus phi? Because it's a the circuit is more inductive, so current is always lagging by angle phi with respect to voltage, where the value of phi is equal to tan inverse XL minus XC divided by R. Right. So again you will find the average value of power P is equal to VI cos phi. This is the same term as we have discussed earlier for RL and RC case. Now if you check about the axis component is VL minus VC, and from then able to find the angle phi. Right, now if you define the case number 2, you can see the phasor diagram where on negatively y axis you can see the vector VC minus VL and the resultant value of angle which is minus phi. Tan phi is equal to VC minus VL divided by VR. Right, so here phi is equal to tan inverse I in bracket XC minus XL divided by I into R. So you will find the resultant value of angle phi, that is equal to tan inverse XC minus XL divided by R, where you can see VC is greater than VL. Right, so I can define the relation of voltage and current is Vt is equal to Vm sin omega t, and I is equal to Im sin omega t plus phi. Now plus phi, that means here current is leading by angle phi with respect to voltage V, where you will find the average value of power P average is equal to Vi cos phi. Average value of power remains the same as it follows the RC series AC circuit. Right, from this now we take the case number 3 where VL is equal to VC. So I can say here XL is equal to XC. So what does it mean? Where both the vectors are going to nullify each other effects. Right, so now circuit becomes purely resistive. So simply here if you apply this in this particular circuit where the voltage across inductor and voltage across capacitor both are same, so I can say the reactance offered by the inductor is same as the reactance is offered by the capacitor. Right, so here VL is equal to VC, that means XL is equal to XC. Right, so from the impedance equation Z, see here you can also see from this phasor diagram where the above phasor diagram shows that VL is equal to VC. That means vector of VL is in a positive direction and vector of VC is in a negative direction. Both will nullify each other's effect. That means the resultant phasor diagram is only VR. So I can say here the circuit becomes purely resistive circuit, purely resistive AC circuit. Right. So if I apply here, since XL is equal to XC, so I can write here XL minus XC is equal to 0. So the impedance Z is equal to under root R square plus 0, hence it is XL is equal to XC. Right, so I can write here the value of impedance is nothing but the value of resistance which is connected in a RLC series circuit. Right, so from this I can be able to say that the circuit becomes a purely resistive circuit. And if I apply this formula where IXL is equal to I into XC, you can see VL is equal to VC, where V is equal to under root VR square plus VL minus VC square, or VC minus VL square. Ultimately, your value of the applied voltage or resultant value of voltage V becomes only VR. Right. Thank you very much, student.